speaker number 1, who was formerly working at Red Hat, and he was among the founding team who created the Linux KVM hypervisor. Please welcome the CEO of ScyllaDB, Dor Laor. I'll just mirror the screens. Hi. So thanks for everyone for coming here on your Sunday. My name is Dor. I'm CEO and co-founder of ScyllaDB, and of course I'm here to talk about database. One thing that I really have in mind, and I need to get it out of the system, is that I come from Israel. So if you need a Hebrew translation, then just put this on. And here in the UN, usually Israel is a matter of conflict most of the time. Yeah, that's how things are. But today, I think that at best, the conflict will be which database is suited for the right role. And our database is open source, so I'm really excited because just last week, we talked with users from Indonesia and users from Iran. So there are good things that we can drive in this world, and open source is one of them. So what's Scylla? Anyone heard about Scylla before? Good. So come here for the right place as well. So Scylla is a new NoSQL database. It's completely compatible with Apache Cassandra. So everything that Cassandra can do, we can do the same. All of the good high availability properties. But we come up with lasting performance. A single node can do 1 million operations per second per node, and we can grow that to dozens, hundreds, and thousands of nodes. And we do that with predictable low latency. So I'm super excited about this database, and I believe that it will genuinely change the industry. But as Eric said, there are more things that are more important than databases, and that's of course getting everyone the same chance. We're lucky that we can code, we can sell databases, etc., etc. So if you haven't donated, go ahead and do that. I won't continue because Eric did such a fabulous job and really kudos to you. We definitely need to put more time than doing community things instead of just technology. So Scylla the database. Scylla is a startup. Today we have 30 people on board, based across 12 countries. And it's not because I like to travel. It's mainly because ahead of time we decided to be open source based. Back in the days where I worked at Red Hat, it worked really well. And eventually, if the project really begins to fly, then you get a lot of contributions from others who may not necessarily come up from your own company. So it makes it matters less who are the people that come up with your company, but it's more community work, and that's what we're trying to do here. And that's one of the reasons that we allow ourselves to hire the best talent in the world, and we're not just confined to those who can commute to our office. So I guess for those who haven't heard about Scylla, you got to be asking yourself, another database? Yeah? Are there plenty of databases already? So that's definitely a fair question, and we asked the same question before we began in this endeavor. So the problem is that, like President Johnson used to say, databases today can't walk and chew gum. Each of them have their you get to do your own charting, and there are no good products that are just will work out of the box for you. If you go to the document DB kind of family, then they're good and easy, really easy to start with because there is no schema. But once you begin to scale and you have lots of data and the data changes frequently, then it's really hard to manage. The column store family relevantly have good things like Cassandra, but the problem is that it's based on Java. It doesn't perform well, not in terms of efficiency, not in terms of latency, and I'll cover that. And lastly, there is the in-memory kind of databases where I actually don't call them database because if you write on ice, it's not really a database. So it's good, but they have their own use cases. However, I'm not here to bash the competitors. I'm here to explain how we did things. And we chose to re-implement Cassandra from scratch using our own implementation to provide similar things in terms of high availability and fault tolerance, but really efficient implementation. And that's where we begin. We have really rich roadmap ahead. So there are a lot of good things in Cassandra. Actually, I think it's the best in terms of high availability and fault tolerance industry-wide. It's the best distributed tool out there. And there are clusters of 1,000 nodes running Cassandra, and it's really amazing. It has flexible replication. You can go from 1, 2 to 10 replicas, and these are just local replicas. If you'd like to have multi-data center, no problem at all. You can even have dozens of data centers within a single cluster deployment. There's a rich SQL-like language, automatic sharding, so adding nodes is trivial. Wide rows, you get to have even your own transactions with the lightweight transaction feature. So you get to have eventual consistency and full consistency. Plenty of goodies from the industry and collaboration with other Apache projects like Spark, Presto, etc. So lots of goodies. But if you're going to read what Gartner had to say about Cassandra, it says that more than half of the people who try Cassandra ditch it because of a bad poor performance. And if that is really the case, those who still run Cassandra need to pick a narrower case where it fits them, and many times they'll add the cache in front of it or move transactions for some other database if they require it. And we are here to fix things up. In one sentence, you can think about ScyllaDB as the power of Cassandra with the speed of Redis. Because Cassandra is more than a key value store. It's really a rich database, just slow. So we provide you the best of all worlds. Trying to be humble here with the TM here. And so everything that is there today with Cassandra, we are able to provide that exactly the same. On top of it, we add lasting performance in terms of throughput, in terms of a 99% latency, in terms of auto-tunable database that you do not need to constantly try to tune your way around it. We can scale up with the number of cores, we can scale out with the number of machines. It's really fantastic, and it's all open source. 100% of all of the features that you have are widely approachable for you. So just a benchmark, a common benchmark from Yahoo, the known YCSD one. I won't dive into it because there's a lot of details, and you can grab all of those details and how to set this up on a website. Just in a few sentences, in terms of throughput, that's the large graph. We compared here a cluster of 3 Scylla nodes against different sizes of the Cassandra clusters, 3, 9, 15, and 30. So in terms of throughput, only the 30 Cassandra cluster installation can cope with just a bare 3 Scylla nodes. But in terms of latency, especially the P99 latency, our latency is way lower and constant, while you see the Cassandra latency jump across the board. And we even didn't try to find a situation where it's hard in Cassandra, because there are cases where we can do even 40 times better. It's just an average case out of the box. When we say full compatible, we actually mean full compatible. It's a drop-in replacement. So the CQL language is, the protocol is wire compatible. So we do not use our own clients. You get to keep your own client. The same administration tools still exist. So it's a node tool or KVM and Xen for Cassandra. So the same things still, the same tools still manage the Scylla cluster. And the same disk format was reverse engineered, so you can just shut down your Cassandra tools and on the same servers bring up Scylla tools, and it will just work. There's even tools for doing migration without losing any data. Either a simple migration is when the client duplicates the writes to both clusters, and you can run in this mode for a couple of weeks until you're comfortable. We have our own tool that instead of the clients, we install a small CQL proxy on the Cassandra side, and it replicates all of the writes to the Scylla cluster, and this way they get synced without losing any transaction while you're doing the migration. So where's the magic? So I'm usually quite technical, so I'll explain that. So there's a lot of goodies in Scylla. One of the key points is to ditch the thread approach towards a shard per core approach. The problem with the threads, they're good, but they're not equipped to be that efficient on multi-core systems. So especially now when Moore's law stopped being effective in terms of CPU speed, you can just add cores to the CPUs, then the problem magnifies. And we solve that by running multiple instances of different shards, and each shard is equipped with its own core, its own portion of the RAM, and many times direct access to I/O resources such as networking and disk. And this means that you can scale up, because if you're going to have a 10-core machine, then we'll run 10 instances within that machine. All of those shards are transparent from the user. So we do regular standard cluster-wide sharding, but within each of the nodes, we do another level of shard, which is transparent. And we actually carefully observe all the components of a modern CPU, of a modern computer system, and try to optimize each of them. So if we begin with the network, then we use multi-queues. So each of those shards is independent and can do its own networking without relying on the kernel, for instance. We use pole mode instead of interrupts, because where you go to high speed, then interrupts just get in your way. And many times, if you use Amazon, you're going to see that there's one core which handles the interrupts, and it really gets in your way. We even implemented the user space TCP/IP stack, and it will come in our next generation. So there's you can expect better performance in the future coming out from ScyllaDB. For the CPU, I mentioned the thread per core, which is a subset of the shard per core approach. There's lock-free, so we do not lock. Each core owns its own resources, and so that's why we do not lock. Locking in x86 is very expensive. Of course, if the lock is contented, the other cores need to wait. But even if it's not contented, then the hardware locks the bus, and that's very expensive in large machines. We have a reactor implementation. Everything is asynchronous, and we use C++ instead of using Java. I don't have anything against Java, of course, and I program in Java, but it's not suited for high-speed I/O. In terms of RAM, our shard per core approach already makes us NUMA friendly, so we only access memory that belongs to the socket the CPU runs on, and not the remote memory, which is twice as expensive. We have log structure allocator for malloc. We replace malloc with our own implementation, which is friendly for this approach. We use zero copy. With the disk, we use direct DMA. We do not use the Linux page cache. We wrote our own cache. Of course, we do log structure merge tree like Cassandra, but really efficient. And we have our own user space I/O scheduler, which I hope that I'll have time to cover it in the next slides too. So I'm apologizing for going rapidly through all of our design, but if I'll go another layer of in-depth review of the structure of our database. On the left-hand side, you can see Cassandra with all of the multi-threaded implementation, and the problem is the kernel isn't aware what the application is going to do with all of those threads. So while you have a packet incoming on one of the CPUs, let's say core number 10, actually the thread that Cassandra will going to process that request runs on CPU number 11. So you've got to use locking, you've got to use cache invalidation with the CPU, which is really wasteful, and it may not be NUMA friendly. We, on the other hand, run multiple instances per core, each of them equipped with the CPU, the memory, and the NIC access, and we do not have to lock. One interesting question is, what happens is if one of our instances gets a query where it doesn't own the data. In this case, we do not lock like a regular database would. Instead, we forward that request using a very efficient SMP queuing mechanism to the target shards. They do the processing and put the request again in a shared memory location, and the original shard who got the request issues that. So everything works streamlined. We have our own task scheduler because, think about it, we do use the Linux scheduler for scheduling threads, but since there's just one thread per shard, one thread per CPU, then we need to do our own scheduling, the relative actions that the database need to do. So we implemented our own scheduler using the future promise notion. It's widespread today, but it's the scheduler that we wrote is specified for our C++ 14 implementation, and it mostly runs Lambda functions. Each of our cores can run 1 million tiny Lambda functions per second, and altogether that's really effective in terms of CPU processing. I mentioned before caching, so on the left-hand side you can see the Cassandra caches, and Cassandra here, I'm getting to pick on Cassandra, but it's many other applications do the same. So Cassandra relies on the Linux page cache for caching, and Linux is doing really good work with the cache. But the problem is that as your application or the database actually has the best knowledge of what to cache, when to cache, and how to cache, and it knows how long would you need this object to cache, and the Linux page cache, for instance, works with 4K granularity. So if your object weighs just 100 bytes, then you lost 40 times more memory by using the Linux page cache. It's also quite complex to configure because there are so many caches there, and the JVM, not to mention that. And if you got everything right, once your workload changes, then you'll need to do everything all over again. Instead, we have one gigantic cache. If you have, let's say, a 128 gigabyte machine, we'll take 120 gigabytes of the whole machine and automatically manage them. I mentioned before our I/O scheduler. We do that in user space. And the reason that we do I/O scheduling is because there are different types of I/O consumers. There are regular queries, there is the commit log, there are a lot of background job processing like compaction and repair, and streaming, and multiple jobs all competing for your I/O. Now the trouble is, if the application or the implementation isn't sophisticated, then you're going to throw all of this processing on the file system and the disk, and they can sustain some level of parallelism, but if it's more than the point that the database can hold, then you'll just get blocked by the disk. But you're going to have a mix of foreground, low latency jobs competing against background, not latency sensitive jobs. And that's really a problem. And if you already issued all of those requests to the disk, then the disk doesn't have anything to do but wait and process them. They don't have the knowledge of prioritization. That's exactly what we do with our own I/O scheduler. Before Scylla runs, we run actually a tiny benchmark which measures the level of the disk parallelism. And we get to issue, let's say it's 100 parallel requests so that can live all of the time, and the disk can serve them with an adequate latency. So once the number of I/O requests goes beyond 100, we queue them up and we prioritize them according to our criteria and not the file system or the disk criteria. Status. So we're open source from September last year, where we went out of stealth mode and published our beta. In March, we released our 1.0 GA. It's still early, but it's very, very stable, and I can say that without hesitation that if you compare the stability of Cassandra or some other databases with us, you'll find it's very stable. We run on physical, virtual, and containers, and Spark, Presto, time series databases work on top of our database because it's just wire compatible with Cassandra. Our next release, we release a new version each month to the open source. Our next release will handle wide rows really, really well, way better than Cassandra, and way better than we dealt with them before. They implemented the last compaction strategy, and we're going to have in the future some others in the future. There's tracing built in, so it's really mature, although it's young. And we have long, fascinating roadmap ahead with a lot of improvements in terms of the core database, like multi-tenancy. And I'm speaking about true multi-tenancy, where each tenant has its own SLA, and you can run on a single cluster, you can mix and run an analytic workload as well as real-time workload. We're going to use the very same tools that we used before for user space I/O and for networking and for CPU scheduling, and that will help us to do a true multi-tenant implementation. We'll go up vertical and grab some piece of analytics and get it near the data, and we have some more horizontal ideas as well. It's also a good opportunity to announce our upcoming Scylla Summit. In 2 months' time, we're going to have our first user and developer summit in San Jose, California. There's a bunch of companies that will participate in that summit. We use Scylla today, and there is even far more than what we have here in the lower page. How to interact. So our favorite is download and GitHub. But be our guest. There is Twitter, and you can take a look at the source. Beyond the database, we have the engine that is the heart, that runs the heart of the database, is called CStar, and it's really good for a bunch of other use cases. If you'd like to develop an object store, or like to develop a really fast cache, or plenty of other usages, or maybe want to take a stab of re-implementing something like Elasticsearch, then it's possible to do that with the engine. It's a separate project,